tall order. Sounds great. I'll start this out by saying that I'm absolutely terrified to be here. And it's not the number of people. And in fact, I've talked to a number of you. This is a great group of people to talk to, bounce ideas off of. Fantastic. You give yourselves a round of applause for just being good people who care about really important things. What is terrifying is that this represents also something like 10,000 years of building science experience, construction experience. It's a tremendous amount of knowledge here. And as someone who's relatively early in my career, I heard earlier this morning that this is the pinnacle. Everything's going downhill for me from here on out. So this makes me a little scared. But we've got a great topic today. It's one that has some history. We're going to talk about that history with magnesium oxide based materials. Where has the world come through with these? Where are we at right now? And some actually really exciting things that we're doing moving forward to better understand these materials. Briefly about the two of us, we are both currently working for DuPont. One of us has way more experience in this field than the other. And in fact, he made me line by line talk through all the cool things that he's done in this space. Because he's got experience with Building Science Corporation, most recently at RDH. He gives talks, or is an adjunct professor. Lots of experience. I think many of you know Aaron Grin. For myself, my background is actually starting outside of the building construction space as a material scientist, and I've been bringing that into and applying the principles of material science into the building construction space and learning a lot about how buildings are built. My natural environment is not in a suit or nice clothes in office. I love to be on sites, learning about how buildings are built and contributing to that. And then here's a picture of me in my natural habitat on top of a mountain. That's Mount Hood in Portland area, just Saturday actually. So a little bit about us. Today we're talking about a new or new-ish building material. And I wanted to kind of structure this or frame this for you guys. I had to think about this. We don't have that many brand new materials show up, and we have to figure out what to do with them. How are they going to work? How are they going to fail? So what we're going to scope this today is to say anytime something new comes along, there's a promise. And this is what the sales guy is going to tell you. He's going to say, oh, it's amazing, it does this, it does this, it does this. And they're not going to tell you anything about the box. Okay? The box says any new material that any material at all has a failure point. You can pull things to the point that it fails. Steel will fail. And so learning what is that box and how close that box is to real conditions that exist in the world tells us how valuable is the promise. The promise is what we think it can do and how it can add value to what we do in building construction. The box says this is where you can use it safely. You go outside the box, you're going to have problems. Okay? So as we talk today, we're going to be talking about both of those things. We'll give you a little bit of primer on magnesium oxide materials. In fact, before I go there, raise your hands if you've heard of or heard the words magnesium oxide as a building material. Okay, many of you, good. We're going to make sure that you're using the right terminology. It's new enough that we're kind of throwing out words. Let's talk about it right. Let's understand what we're talking about when we say things. Then we're going to talk about a little bit why it's awesome. That's the promise. What value could it bring? We're just going to sound a little sales pitchy, but let's just honestly look at how could this be useful to people who are thinking about the building envelope, exteriors of buildings. But then we're going to look at the box and say, where have people used this outside of the box? And they had problems. What were those problems? And how are we now either both enlarging the box, making a better product? I say we, I'm actually referring to a lot of people who think about magnesium oxide boards outside of DuPont. It's not just us. And then how do we make sure that we help people stay inside the box as they're using this product? And really this box, we're working to better understand it through a lot of both accelerated testing and real life test hut-like things we've talked about earlier today. And Aaron will be the one that really dives into all of that real-world accelerated test hut type testing. So, magnesium oxide. You've heard of it, but what's interesting is that magnesium oxide is really the starting material to make a wide variety of products. So magnesium oxide is used as chalk. Climbers, if you see those little white marks on the walls from them going up, it's magnesium oxide. Used in food, cosmetics, etc. As it's made, which is actually magnesium carbonate. That's how it's dug up out of the ground, as chalk. We take that material and then heat it up and turn it into magnesium oxide. That's a raw material that we'll use to make materials, make cement materials. And that, even as a raw material, is used in a variety of different places. Some are noted here. The magic really starts when you take this magnesium oxide powder and you mix it with another ingredient, magnesium chloride, magnesium sulfate, or magnesium phosphate. When those come together, they react and form a cement. Not unlike other cements that you're familiar with, Portland cement or gypsum type materials. That's the reaction of salts that come together and form a crystal. But that isn't even what we're using here. Because that material, it's like a ceramic. You could make a plate out of it. It's been made into billiard balls, things like that. It's a very, very hard, dense, and not particularly usable material. So where it really becomes interesting for this group is when we turn it into a board. So these are commonly referred to as MgO boards or MgO panels. But even amongst those, there are different types. So I have here magnesium. If it's made with a magnesium oxychloride cement, we would call that a chloride board or an MOC board. Alternatively, we can MOS or sulfate board. Phosphate is not yet really commercialized material in these boards, but could become. This is a developing field. People are making technological advances here. And then once you've made these boards, they can be used in a variety of different applications. Today, we're just going to be talking about exterior sheathing and its use in that application. There's other people who could talk better about how they're being used in a variety of other different applications. So the fact that we have to incorporate the cement into a composite board is really important to the properties. Now, our ability to do that and to get the benefits of all the different materials that go into a board depends on adhesion. In a large part. We talked about that earlier today. I had a great presentation. I'm not going to obviously dig into that level of detail, but the compatibility between all the different phases allows us to make the type of board that I'm going to talk about with the advantages and the properties that it has. So, what makes up a magnesium oxide-based panel, an MgO panel? At large scale, what you're thinking about is a fiber cement composite. So it's got layers of cement material intermixed with layers of fiberglass that give it the strength. I'll talk about that in a bit. As you zero in and look at just the cement part of it, that itself is a composite, generally of cement with some other additives and fillers that aren't there just to fill up space, like fill over the cylinders. They actually provide a very key function in the panel itself. And then finally, when you zero in very closely, it is made of an inorganic crystal material. And this inorganic crystal is where some people start to go outside the box and make materials that weren't right for the application and were used outside of the box. We'll cover those later. So very briefly, I think you have an intuitive sense of what fiberglass reinforcement does to the material. You won't find any magnesium oxide boards without some sort of fiber reinforcement. They just wouldn't be strong enough to be used appropriately. As we start to zoom in again, now this composite that includes both a matrix, that would be the magnesium oxide space cement. You can see in like the red picture, that's where all the cement is, and then all the non-color stuff, which is covered in the right image, those are the fillers, which generally include wood and perlite or some other low-density inorganic material. Now, the use of both of those, I'll talk about why they're important later, but they do contribute a lot to the toughness of the material. We talked about in the adhesion presentation earlier about how the ability of the material to deflect and move stress around is really important to making a non-brittle material, and that's how that's used here. Okay, let's zoom all the way in now to the crystal. I'm going to be talking about this, and this is really the first slide that I'll talk about chemistry. So don't glaze over. We're not going to do an hour of chemistry, but let me just give you a little insight into what's happening here, so that we can understand later on the ways that these products have failed in the past and how we're mitigating that now. So this is a cool picture that actually describes how molecules of magnesium, water, and chloride end up organized around to make a very hard, durable material. Now, this is a self-assembly process. You just mix them together, and they just magically do their thing. But what's complicated is that they can produce a variety of different arrangements. So the person who's making this board has to know the process. I'm going to talk about that a little bit later. You guys don't have to figure that out. That's what the board manufacturers and board distributors, they need to understand how do you make the right board, how does it have the right organization of stuff so that it performs in the expected way. So amongst the magnesium oxide chloride and the magnesium oxide sulfate boards, it's generally established, both in the academic literature and in a lot of industry testing, that a particular version of those boards is what gives the best performance. It would be called phase 5 with the magnesium oxide chloride and phase 517 for MOS. You don't necessarily need to know those numbers in particular. However, just know that if someone's making a magnesium oxide chloride board and they haven't controlled how it's made, they could have any variety of different things inside that board and it will not perform as well as the high performance phase 5 boards. Same thing goes for an MOS board. Now, just comparing MOC and MOS, both of these materials have advanced fairly significantly in the last 20 years in our ability both to understand academically why they behave the way they do and how to produce the board with a particular composition. And there's slight differences. I highlight here ways that the MOC boards seem to generally perform better, those that are well made, compared to ways that an MOS board, well made, performs. And these are, we'll call these slight differences. And the particular manufacturer, distributor board would have to share how these perform in these ways. So I mentioned advancements to how these boards are made. Here's a quick overview of what happens. I think this is fairly intuitive. You mix this stuff together, pour it out into a sheet. But what's been learned is that how these products are cured, as well as the ingredients that go into the mix, are super, super important. And early on, they thought, oh, I just throw it all together, throw it into board, ship it out, it's going to work just fine. And that wasn't true. Now we're doing a lot more a lot more understanding has come in about how to mix, how the ratios work, how to cure it in the right way, even ways in which we store it. I mean, early on, these boards were just stored outside in the weather for some period of time. They thought, oh, they're super stable to water, which they are quite stable, but 6 months, 9 months in the rain did not do well for them. So we've learned a lot about it and improved the process. Again, we is not DuPont, we is really the industry as a part, not as a whole. I'll talk about that in a bit. Okay, so the next couple of slides are really focused on the promise. So if you've heard about magnesium oxide and you're wondering, why would I consider that? Here's a couple of slides that highlight the value that this can provide to a project, and then we're going to talk about the box. So first of all, magnesium oxide-based materials perform very well under fire test. Now we'll note that many of them are not considered non-combustible. They do have some amount of wood in them, just enough, barely enough wood that if you run an E136 test, it doesn't fail, or it fails that criteria. It's not considered non-combustible. However, because of the way that the material behaves in a fire event, in NFPA 285 testing, in E119 testing, etc. It really does well. And here's why. Early on in the fire, the wood that's present, it oxidizes. It does generate a small amount of heat, but that's counteracted by the fact that this board, because of the water that's incorporated into the crystal, and the cement, plus other water that's in there, it's about 40% water. So when it starts to get hot during one of these tests, a lot of that water is evaporating, it's keeping the material cool, and what's left behind is 100% non-combustible. Magnesium oxide as a raw material, or mineral, and the glass fibers. And so I've highlighted here a number of different tests, and this is just relative to the DuPont products. Other products I think are similar in terms of their ability to perform well in hourly rated walls and in NFPA 285. Okay, this is where I think the magnesium oxide based boards really start to shine. So these products can be used as a direct structural nail or screw base for most cladding types. And the reason you get that is, most cementitious materials, you try and screw into them, they're quite brittle, and they'll hold a little bit, but they'll break apart as you put a fastener into it. And if you try to increase its toughness, decrease its firmness, it becomes too weak to actually hold fasteners. MOC cement, I talked about that on the first slide. It is a very, very, very strong material. In fact, it's much stronger as a cement than Portland cement. So as we start to add these additives, wood, perlite, the overall strength of it starts to drop. But because we started so high, the final composite panel still has a lot of strength, but it also has toughness. So you can put a screw into it, it's not going to shatter, crack, and it's going to hold a significant amount of force. So I've shown here, this is an example pull-out test. Just putting a fastener in and then just ripping the fastener out. The specification that DuPont uses is something like 280 pounds of force to remove a single fastener. But when we start talking about design criteria and actually putting on cladding, we're operating at below 100 pounds force. So look at that curve, think about how much force it takes to actually pull that out, and we're operating in the very bottom end of that stress strain curve. So very strong, and so now because you don't have to go all the way back to studs, this simplifies and gives you more flexibility in attaching cladding to the outside of the building that's been clad with this product. A couple other things. The early interest in this material was really driven by its response to moisture. That is, its ability to move moisture around inside of the board. If you get a point source of moisture, it's able to move that water around, and then able to release it back into the environment. This is some data showing from the testing firm Built Environments, where they were able to show that even a fully wet board on the right graph is able to release water even faster than, for example, some of the common wood-based products, plywood and OSB. But on the flip side, it's able to act as a reservoir for some amount of water, absorb it from the atmosphere, and then again later release it. Last thing, starts to get a little bit towards the box that I've been talking about. It is stable to repeated wet-dry cycle with bulk water. On the bottom left here shows a graph of what you'd expect the dimensional stability of this to be after a number of wet-dry cycling, showing that MgO, even after it's been wet and dry 25 times, is still the same, functionally the same size when it started, compared to the well-known phenomenon that OSB continually gets thicker and thicker as because of the movement of the materials inside as it swells and then shrinks again. Now, let's start talking about the box, and we'll go into this. It is not stable to unlimited amounts of water. And I have a graph here. This is some data that we collected in the lab, where we soak the board fully wet and then heat it to 70 degrees Fahrenheit. We do start to see the phase 5, that's the stable structure that's holding us together, starts to degrade. So that's one of those warnings. I said, okay, there's a box here. We can't expose this to unlimited amounts of water and unlimited amounts of heat and still have it be stable. Oh, Celsius, 70 degrees Celsius. Sorry, not 70 Fahrenheit. Yeah, that would be that would be too small of a box. Okay, so let's think about this. The promise, I've talked about the advantages. Fire performance is great. The ability to put cladding fasteners directly into and hold directly off of the panel instead of move back to studs. That's a real advantage. That's the promise. But what about this box? And in particular, there's some very well-known failures that happened about 10 years ago in Denmark. And in this case, people had, they were super excited about this material, and they're putting MgO-based panels onto the exterior facades of buildings. And they said, hey, these are super stable to water, so we don't need to put a WRB on these. This will be our water-resistant barrier. And they said, oh, we can just source any boards. They're great boards, they feel great, so we're just going to go buy the cheapest boards we can find. And install them, and they had problems. Now, what's in the title, you probably saw the no sweat thing. That's a weird thing to talk about with building materials. But literally in this case, they were seeing creation of water droplets on the back side of these panels in use. So sweating was one problem. I'm going to talk about what that is from a material science perspective. And they were also seeing corrosion from salt that was leaching out into these droplets and were causing problems. There was also mold issues because of this water around. So really not a good situation. So what's going on here? So first of all, sweating. What does this even mean? What's going on is that the balance of materials inside, the stoichiometry or relative amounts of this stuff was off enough that there was enough magnesium chloride that, like sugar, it absorbs moisture out of the air. It's hydroscopic, would be the word we'd use. It simply grabs it from the air and turns itself into water. And I think you guys can appreciate this. You've seen a lollipop stand on the ground. It's basically, or a Jolly Rancher, right? In a hot, humid environment, that thing will turn into just a puddle of sugar water on the ground. It's a similar concept. Magnesium chloride, when it's just sitting there, will absorb water to the point that it becomes a drop of water. The picture on the right is a sample that was purposely made poorly to show you what happens in that case. So how did we get there? How did this happen, and what did we learn from it? So first of all, having the right balance of ingredients is super important. And in the past, we're talking about factories where people are measuring stuff out by shovelfuls. I need 6 shovelfuls of this, I need 7 shovelfuls of this, and that's my board. That's clearly not precise enough for the type of chemistry that's happening here. And so improved processes to make sure the right amount of stuff, make sure everything's reactive the way it's supposed to be. And the other thing that we learned is that even a well-formed cement structure can fall apart without appropriate additives. There's been a lot of academic research into that, and they discovered that there are very stable forms that can be created through the use of specific additives. There's a number of patent literature and academic literature on that. And so neither of these were practiced in the case that I just talked about and in a few other cases. So what we learned from that experience is, what's outside the box. So first of all, boards that are made without the kind of quality control and understanding of the process to make a high quality cement. That was, number one thing that's going on. The fact that they had no supplemental, no water resistant barrier on the outside meant the water was wholesale getting in, moving around, and able to start degrading the cement structure. Fasteners were all unprotected, so even when there was the risk of corrosion, the fasteners corroded very quickly without any protection on them. And then even on the inside of the board, the fact that they were exposed open to the cavities meant that without air sealing, which there wasn't air sealing in these buildings, moist air could leak in, get into the cavity, hit the cold backside of these panels, condense water on magnesium chloride, and cause the issues that we saw there. So all of these things all happened together at the same time to create what we'll call a very worst case scenario. So what have we learned since then? We have to address all these. We've got to operate inside of the box and avoid these conditions. So let me talk briefly about what that might look like. First of all, we have to start with a high quality board. I have a couple of slides on that and what that might look like. There needs to be a water resistant barrier. These aren't meant to be WVs by themselves, or the water control layer of the board. It's got to be outboard of that. Adding interior vapor throttles also helps mitigate the presence of high humidity on the backside. That I'd say is almost unnecessary given the other conditions that we have, but it's an extra layer of protection to make sure that we're not building up water inside the boards. And then finally, the fasteners are selected for being resistant to corrosion and are also treated and protected from liquid water from the outside. All these things need to be compatible. I show a couple of pictures here. Not all materials stick to magnesium oxide-based materials. You can see the, is the picture on the left, is that adhesive or cohesive failure? Who was listening earlier today?
Yes.
I love it. Yep, that's an example of adhesive failure. The material just is not sticking, and they separate right at the level of the coating and the magnesium oxide. You can see on the picture on the right, it is cohesive failure of the substrate. You just tore the board apart when you try and rip off the WRB. Similarly with the putting foam onto the backside to make an integrated board has advantages by creating a vapor control layer behind, so there's not a free flow of vapors to the backside of the boards to get a lot of water inside. And then the fasteners, like I said, we want those to have treatments, be resistant to corrosion, to be better prepared for that. So, talking about good boards. This is a tough issue because the reality is this group shouldn't be the ones that have to go out and make sure that the board is good. So, my warning, first of all, is that not all boards are created equal. Some people know what they're doing, and some people don't. Now, to deal with that, obviously, how do we deal with that in this industry? We create standards. We create tests that allow us to identify and verify whether a board is good or bad. There are some standards that are coming out at XXVI because that standard is still being written. But there are organizations and groups that are involved in creating those. The HC386 from ICCES, that is in place, and people are testing and showing compliance and being able to make really good boards. You can see in the requirements for that, freeze-thaw cycling, the ability to maintain structure as it gets wet and dry, water absorption, how well does it absorb water, which is related to how much chloride is around, and then also corrosion and corrosive effects. But beyond just simply the standard, that standard says that a distributor or manufacturer made one good board one time. The question is, what about every board? Are they coming out? Are they uniform? Are they complete? Are they good? And so, as you look for sources of these boards, they should be doing quality control themselves, not just for the person that they're sourcing it from. Asking, if you put it in high humidity, does it sweat? Have they balanced the stoichiometry and the mix of reagents right so that you don't see that condensation effect? Also, if you crush it and try and leach out the chloride, does it leach out? How much is there? Once again, are they making their board right in terms of their process and mix of ingredients? And one slide I wanted to highlight. This is from a project that happened over in Maine, just to give a sense of how does this material behave when it's out in the open, exposed to the environment, and getting wet, getting UV, etc. So this particular project, armor wall panels were installed and left exposed for about a year or so, which I'll note is longer than what we, as a manufacturer, recommend being exposed, but we all know that those get exceeded more often than we'd like to think they do. But this allowed us to go and say, worst case scenario, lots of water exposed without cladding for 12 months. And what we looked at is, number one, do we see any evidence of corrosion? And we took pictures around, and really there was no evidence that either the steel framing or the fasteners had any corrosion on them. We also have ways to analytically break apart these boards and look to see whether the phase 5 structure, that's the core cement material that's holding all this together, whether it's being degraded over time or whether it remains. And that the graph on the bottom tells us that the phase 5's content in this material, it's stayed constant the entire time that it's been exposed to the environment. So some early indications that it's really behaving much, much better than the Denmark boards and reflects advancements in board manufacturing and the complete system with a WRB and footwell in the back, et cetera, that make this a much more robust system. So start to transition now and to say these are some basic product evaluation standards, et cetera, that we need to meet to be able to convince ourselves that a board we're using is going to perform as expected. But what about beyond that? How do we predict whether material that's been around for 10, 15 years is going to behave well for 50 years, 60 years, 70 years? And there's been work going on both in academic labs and internally within DuPont to really push these materials farther, harder than we have in the past, and make sure that they're performing well. So I'm going to turn that over now to Aaron, who's going to talk about some of these testing as well.
So I guess to start, I'd like to thank first Betsy and Joe for the opportunity, but also for Hardwig and Brian for already gave a presentation about test beds. So I used to work for Joe, and one of the very first jobs I did was go down to a research test hut in Florida and put in probably something like 500 to 600 sensors. That was my very first job, and even back then, you can see that the Dow styrofoam was being used right next to home wrap. Now, they were competitively testing against each other, but it was there. The one on the right, the one on the left lived its life and then was demolished. The one on the right is still in Portland. It's at a different site now, but again, in a relatively wet climate, looking at direct applied stucco, seeing what stuck, what came apart, what rotted the wall behind it. And that's me in the bottom right corner. They're actually installing the Tyvek. The one, who recognizes that back here? The one on the left. So that was a mock-up we did one summer. And if you look really closely underneath that window, it's one of the preformed Dow sills being covered up with Tyvek. So another overlap. And then the one on the right is the Florida test bed. I've been told that we still do sell that product in relatively small quantities, but just having fun on site installing stuff. So like Adam, I like going to build stuff. The box on the top left is what we called the thermometric chamber at the time. I spent probably close to 1,000 hours a year for like 4 years working on that box and building it and commissioning it with Chris, who's down there on the right, John. And then we wrote some papers about that, and some other people got excited about the papers and the ability for them to have another armature chamber. So the one on the lower left is a 3-sided field exposure facility in Toronto for a college. The one on the right is another school in Toronto, and it's a roll-apart climate chamber, but it doesn't do R-value tests like a thermometric chamber. And then in about 2016, Carleton University came to us and started to ask questions. They wrote us a dream list of things that they wanted to test. Some of them were crazy, and we had to dial them back a little bit as to what they could do. Like we can't do 10,000 pascals of air pressure differential inside a guarded hot box while measuring R value. But they definitely wanted to do masonry retrofits. So that's a masonry retrofits, but also wetted masonry retrofits. They wanted to have solar power in there. So Okay. I have a few more pictures of that facility later as to what we're actually doing with them, because it took until 2023 to actually have it built and commissioned. So now that I'm working for DuPont, I set up an and research study with the university, test MgO and armor wall products. So Midland Outdoor Exposure Facility, it was about 2010 that Dow approached us to come build pretty much the biggest and best hut we've ever built. There's another one of these in existence now. It looks strangely similar at the University of Waterloo that John Straub has to work with. But this one, we coined as Taj Hut, just because it was the biggest and best one that we've ever made. It has 7 walls per orientation. The wall openings are 4 foot by 10 foot, but it is a post and beam frame so that we could have 10 foot by 12 foot openings. We could take out the little dividers in between and do much bigger things if we wanted to. On-site weather station, we have the ability to pressurize it, depressurize it with air. It's got about 800 sensors in it and a data acquisition system that will let us monitor temperature, relative humidity, moisture content, and heat flux in any one of the walls. So we built and commissioned that between 2010 and 2011, and it's been running since. And there's 3 residential wood frame walls in there on each orientation that now we have 15 years of runtime data for, that have vinyl siding and adhered stone with and without exterior insulation, vapor permeable WRB or not, to see how they run. So I'm hoping that between Adam and I will actually get to write up some of that. Now there's like 15 years of data sitting there. So there it is. Last time I was there, like a month ago, I took my drone and snapped some pictures. Inside the test facility, that is during construction the first time. The guy in the middle there is Gary Parsons, if some of you remember Gary. The data acquisition systems on the right, there's actually another piece of data acquisition up there now. So there's Campbell Scientific data loggers, Campbell Scientific multiplexers, and there's 7 32-channel multiplexers on each logger. And then there's another one added now for heat flux. So what did we do this time? Those are the walls that got finished in November of 2023. And on each orientation, there's 4, 1, 2, 3, 4, pretty straightforward. We had an awkward naming convention before, but we fixed that, some labels. So we have wall assembly 1, because we wanted to get more information out of the study, because everybody wants more information about this stuff faster. Instead of doing 4 foot by 10 foot walls, we did 4 foot by 5 foot walls, and we doubled up in each test bay. So instead of opening up and doing 1 big wall, we doubled it up. So we ended up total building 32 wall specimens to test on different orientations. And this is the first one. So just as there was a whole bunch of work around the very first pictures with Teresa Weston, doing what does inward vapor drive do to OSB, and how do we make sure this is safe and what works, right? That's the purpose of this test. We wanted to look at that over armor wall. We chose to choose 2 options, opted to choose 2. One is a vapor open assembly but drained. One is a vapor closed assembly and drained. So both have drainage in them, like there's nothing squeeze direct applied, but one's vapor open, one's not. One's slicker max and the other one's delta lath. So the other thing we do on the outside of these test walls is to put, we call it wetting apparatus. It's really just shop towel attached back. In the armor wall case, we didn't want to be nailing through the WRB, so they're actually taped on the sides. And then we're able to, from the inside, directly inject water into that drainage space. So I can say, I'm going to put in 100 milliliters of water, and it's going to go right into the drainage space as a worst case scenario. Wall assembly assembly 2. It was split upper and lower again. This one's metal panel cladding with a gap, like super typical. I think that's an old Kingspan product that we had in the lab. And then 2 versions here, the Armor Wall 2 3/4 inch product on a 2x4 stud, all steel stud by the way, for these, because it's a commercial product. And then on the outside, we don't even sell armor board for this application. We only really sell it to wrap rough opening prep. But I wanted to do a worst case scenario, so we put just 1/2 inch armor board on the outside of the 6-inch deep stud cavity, so that we can figure out the temperature and relative humidity conditions, and then getting into the 2nd or 3rd year, torture test them by putting in an orifice plate, pressurizing the space, bringing it up to 50% relative humidity or something, and force air into the assemblies. And then we're going to be able to take all of this off and take it back to the lab and go through any one of the tests that we want. And again, this one has wetting on the outside of the WRP. The 3rd one, we were looking at, the best case scenario, especially in climate zone 2, 1 or 2, is just use all continuous exterior insulation. Don't even bother putting stuff in the base because you're kind of wasting your money. So the upper one is empty 2x6 with our product on it, and the bottom one's an insulated, again with our product on it. And we can do air leakage on that. Then we wanted to look at recreating the initial issues that MgO had in vertical applications. It had old issues in roof applications. But this one, we wanted to recreate the Denmark one, and one of the issues with Denmark was like the height of the cavity, and we didn't want to play with that. So I didn't do a horizontal split on this one. I did a vertical split. And then what we did on this one is we took the bare MgO product, so we did what they did in Denmark, and then one right next to it with the coating on it, the WRD coating. And then, again, we're going to force test these with an orifice plate. So here's how they look going together. All taped up. There's the bare white MgO board right next to the Armor Wall product. The orange things are the wetting apparatus, and that was for the stucco installer because I didn't want it to nail through my wetting apparatus or the sensors back there. I guess that's something to point out here too, is all the diagrams on the right there. Oh, you can't see my pointer. Shows the wall section breakdown, and all of the blue sensors in there are all the temperature, relative humidity, and moisture content sensors. And then putting it together, again, punching in the wetting apparatus, putting the Kingspan on, just about everything you would do in real world, right? So this is what Hartwig was talking about this morning with getting to real scale. Like we've done it in the lab, let's get it to real scale, and then we can torture test it all we want. And then that one was just the last 2 test walls. We didn't have the type of cladding that they had in Denmark, so we kind of used a fiber cement surrogate, but we chose a relatively uncoated fiber cement so that even if we wanted to, we could put a sprinkler on this thing on a timer, so it just gets hit with a sprinkler every morning or something. We can do some fun torture tests with it. And then, what does that mean? So that's a graph, and this is the level of data that we get from every wall, and that's from when it started up in October. You can see in early October, the temperatures start to split and separate. That's because we actually got the insulation in the walls. So the sensors were getting cooler and cooler on the outside. And then that, like 14 sensors, that's just the temperature data for every wall. We also have relative humidity data and moisture content data for everything. So early season takeaways, that is November to May, and this is the stucco wall. No, this one I was looking at, sorry, this is wall 2. The stucco wall's next. What I wanted to see on this one was the MgO that's bare on the lower 2x6 versus the 2x4 with Armor Wall Plus that has insulation on the back of it. What's the relative humidity at the inside surface of that which would be the worst case scenario for air leakage condensation to the back of it. So I wanted to see what the relative humidity, what is our humidity baseline now versus when we start injecting air. So that's the difference with and without exterior insulation. I know it gets harped on at this conference a fair bit. Exterior insulation works, and there's just a quick snapshot of some of that. What does it look like from a thermal analysis? So this is the air leakage condensation potential. So this winter, one of the other things that we can do is mess with the RH inside the test hut. And so for this winter, it was running at 72 and 40 RH. So that's something like an 8 or 9 degree dew point. So that's the red line. So the wall with exterior insulation is the green one up top. And the wall without exterior insulation is the lower line. This is hourly data. So between November and April, for every spike or duration that the orange line is below the green, that's an hour of possible air leakage condensation if and when we inject air. Because we do build these test walls pretty tight so that we can do this baselining to say what's the humidity, what's the temperature, and what's your risk profile. And then looking at the actual relative humidity on stucco wall 1 to try and figure out, even if it's a drained space, the vapor impermeable that stops inward vapor drive, how does it affect the cavity space relative humidity? And so the orange ones are the vapor permeable system. They have fewer drier hours and more wetter hours than the one that has an impermeable layer to stop that inward vapor drive. That's the blue one. So interesting data, readily available over the winter, which was fun. I'm curious to see during the summer what happens, because this area of Michigan does have some pretty humid times, and it does rain, and then the sun comes out. So what's going to happen to these cavities, and how does this graph shift over time? And is there like a risk area here or not? Okay, so coming right off Hartwig there, what are we going to do now that we have all this data? We're going to take it back because this is a climate zone 5 application. It does rain, it does get sunny, but it's still climate zone 5. So people ask questions. They say, well, what does it do in Portland? What does it do in Miami? So we're going to take this, we're going to tune the models properly, and then we're going to be able to switch the climates around to get a pretty good feel for how it all works. Then we're going to add air leakage and add water leakage. We're going to see what happens then, recompare the data again, and then we'll pull the walls out and take them to the lab. But depending on how safe or how good the data looks, we can really start to torture test them with more water or more air or higher humidity, just to see what happens. So then the other project that I mentioned at Carleton, well, they're showing up in a funny order and I don't know why. So that big box will test up to a 16-foot by 25, 15-foot, 16-foot by 25-foot wall specimen. So it's huge. And it'll hook up to 2 feet deep with whatever we want. And it can be as heavy as a CMU wall. So their overhead crane is sized to do the CMU wall. So we're going to get more data again. And because the walls that we're already testing are, oh, that's not me, 4 foot by 4 foot, we're going to break this thing up into a 3 by 5 grid and be able to test 15 walls at a time. So this is why I'm calling it pretty short term, pretty high value. We have their climate chamber for, I think, something like 2 months of time. That's what the research piece is. It's going to be like 8 months of getting it ready and then 2 months of testing it. And we can mix and match any wall we want. Yeah, I don't know why they're coming up. So the overall capacity of this thing is crazy. Like Chris and I spent a lot of time working on the design for this. And then even during COVID, I was back and forth to Ottawa, checking in, being QA/QC on site, answering questions. So it was a fair bit of fun. Lots of options in terms of what we could do with it. Like it has air pressurization, depressurization. It's got a 20,000 watt light rack that recreates the sun, not from UV, but the heat. It's programmable to do cycles, so we can ramp it up and down, like it's not just steady state. And then we can also take this entire rack, it can get picked up by the overhead crane, taken over to the pressurized spray rack, and we can soak all the walls, and then put them back in and see what happens. And we can do freeze-thaw cycles after we do the wetting. And then again, we're gonna put all those 4 foot by 4 foot walls back on pallets and send them back to the lab to take a look at everything. So this is the overall scale of that box. Cynthia is standing in the light blue shirt. She's not short, particularly. It's just a massive box. It rolls apart, as you can see in the two middle pictures. The one on your right is what we call the guard box and meter box. The one on the left is the climate box with the big light rack in it. And you can see on the left picture there how it rolls away. You can put your walls in, swing it back, clamp it shut, and that's how we get to do some good validation verification. And then because we want to also see what the products do with and without fasteners, how they interact with the environment, we originally had the idea to make like a suitcase exposure facility, like something that you could just take on a plane someplace or whatever. But then the ideas keep coming, and you know the way you want to look at it keeps coming. And we came to the idea that it too should fit on a pallet. And we can take this thing, it's screened, vented, top and bottom, so that the samples that are in there can be exposed to ambient temperature and relative humidities in how many are we going with? 4 now? Are we doing more, maybe? And then the samples that are in there are all built in like triplicate or quadruplicate, so that where we send these, we can have somebody go, pick it up, FedEx it back to the lab, and we can test it at 6, 12, 18, 24 months, whatever we want to. So then, this is where we've got them currently. So the Denmark study that had issues, we have a sales guy there who is willing to park that in his backyard for 2 years. So it's in that high humidity environment, and we're gonna get samples sent back. We've got one down in Florida now, obviously one in Midland, Michigan, because that's really easy to check in on. That's where the R&D offices are. And then another one over in a damp place in a yard of a supplier in Tacoma, Washington. So we're basically testing the crap out of all of this to validate that what has been developed with the proprietary coatings on it are gonna work, and they're gonna hopefully work everywhere. That's it. How do we do?
Take some questions. Yeah, go ahead.
Yeah, just an overview. What is this panel used for? What is it displacing? And what are its advantages or disadvantages over what it would displace? What is it used for?
Sure. So the applications we were talking about today are exterior panels. So this would be installed on the outside of framing and would provide both the exterior insulation, the surface that you're going to mount your cladding on, and water-resistant barriers, so air, water, and thermal barriers on the exterior of a, say, steel construction commercial building.
What are the advantages over what's being used now?
Yeah, so the ability, the promise is, good fire performance, which there are a number of materials that have good fire performance, and then structural attachment of cladding directly to these panels, as opposed to having to go through.
You don't have to go back to structure, it becomes the structure.
That's right.
Yeah, and then it has the air and water barriers integrated.
But does it have like sheathing capabilities too, like exterior and lateral forces? Or just like an acreage?
It can, it does. We're trying to figure that out.
Where are you building this at now?
Pardon?
Where are you building this at?
Where are we assembling the product, or where is it being used on site?
Where are you actually using the panel at?
Yeah, where are projects that are happening?
William, do you know where most of the panels are
used? Yeah, I think the answer is everywhere.
Yeah. So I know of projects in Maine, Ohio, Michigan, Denver. Yeah, I'm not a sales guy, so I don't know where these things are actually being used.
It replaces fiber-based gyp. Right?
Yeah. So the intent is replacing fiberglass faced gypsum.
Yeah.
You showed in one of your slides that here,
Thank you.
that the pH value in the boards is around 11 to 12. Do you or don't you have any concerns about long-term stability of the glass fiber mats?
So it's a little lower. I think it's closer to 10 to 11 is the pH. And so the coated fibers that are being used right now are fully stable enough for long term.
Yes, I have a follow-up question to that as well. So there's been a study by RDH and Rockwell that did exterior insulation and showed different fastener pullouts with up to 6-inch or even greater of exterior insulation and strapping. So your half, they were using 3/4 inch plywood to secure those fasteners. With your 1/2-inch MgO board, have you guys done similar studies to see with exterior insulation and below?
Fasteners is something that we're working on a fair bit. We're actually working with TrueFast to have something custom. But in most applications, this has, 2, 3, and 4 inches of polyurethane foam on the back side of it. So it's already got a bunch of exterior insulation. If you had a passive house or something and you wanted to do more on the outside, we'd be willing to look at that, yeah.
Right, okay, so right now it's just that insulation on the interior side of the board and only use the machine to pass the product directly to it.
Correct, but I would pretty easily believe that we have enough pull-out strength with all the data that we have. Like we have 10,000 data points. That system should work because it should transfer the load into pull-out.